nanohub.org.
Online simulation, and more for nanotechnology.
Thank you. It's a pleasure to be here. Thanks, everyone, for coming. So this will be a more light talk compared to probably what you are used to, like not so much on technical details, but more about the company and the process of the research in general. The outline of my talk is that we'll talk a little bit about the company, what we do, so you have a better idea about our activities and background. Then I'm going to spend a little bit of time for two of our main products. One is in the area of laser filtering, which is what we are most known for in the field, and also about the lithography technique to make large-scale nanostructures that we put a lot of effort lately. And this will be the first part of my talk. And in the second part of my talk, I'm going to switch gears and talk a little bit about commercializing optical metamaterial and optical nanostructures. And I'll try to answer the question, how much effort do you need to put to get something from the lab to an actual product? So let me get started and talk about our company. So we were founded in 2010 out of England. We still have an R&D office there. We have two more locations. Our headquarters are in Halifax, in the eastern-board of Canada. And recently, we have an office in California as of this year when we acquired a company specializing in rolling mask lithography. In total, we have 21 people working across these locations, 19 patent families, and we also own the domain metamaterial.com. We have a few collaborations outside, outside the group of Zubin Jacob here. In Canada, we work with Kallos and Eleftheriadis on optical metamaterials. In the US, we have work with Brongersma and Andrea Lu group. And also in the we have a good collaboration with Russia, Itmo University and Pavel Pelov's group. This is for metamaterials for MRI. A little bit about the team. Our CEO, George, who's a founder of the company, along with myself. And I apologize for the picture with the tie. I was forced to put a tie for this photo. It's only the second time in my life I put the tie. The other one was my wedding. And we have in California Boris Kobrin, our CTO, and Brongersma as an advisor to our projects. And the chairman of our company is Maurice Guiton. He's a Canadian veteran aerospace businessman, and because a lot of our activity is in the aerospace sector, as you shall see. The applications we work on, this is just a very high-level overview. Outside the laser filtering, which I'm going to focus more next, we work on thin film solar cells using metamaterial nanostructures to enhance efficiency, and the target market is for aircraft and satellites where thinness and low weight is very important. We also have a couple of patents and activity on metamaterial films to make LED brighter, to extract more light out of the LED chips. We have anti-counterfeiting technology and touch sensor technology, basically transparent conductors that are better conductivity, that allow you to go to very large display sizes. And we also have a side that does medical applications of metamaterials. One of the key projects there is a non-invasive glucose monitor, so to measure glucose for diabetes patients without actually drawing blood. It works with transmission of millimeter waves through the skin. And over there, we have patented the idea of putting a nano coating on the sensor to maximize penetration through the human tissue. And I don't have time to cover this today, but it's interesting work for RF and millimeter waves for us. Before I go on to the more special topics, I wanted to touch a bit upon what's the difference working as an academic versus working in the company, because we do have R&D activity. There are a couple of interesting things. The first is we're a hardware company, a hardware early stage company, as opposed to what many people are more familiar with, which is the software company. So in software companies, the motto is, it's not the question whether you can make something, but it's rather who'll lend you and buy it if you make it. That's the challenge they are facing. This is in contrast to what we are doing, which is, it's not the question whether anyone will buy it, but can you make it well enough or not. That's one key feature. The other is the concept of applied research versus basic research, which is what most universities are doing. So we do applied research, meaning we try to make problems simpler and then solve them, as opposed to what you might do in basic or pure research, which is to make problem harder and then write a paper and then move on. And finally, I want to point out it's much easier to get a result than to get an answer. So in what we are doing, we try to put enough work to get answers, not just get a result and move on. So these are some key differentiations between applied work in an industry versus what you might be used to in a university. That being said, let me talk a little bit about our main project, which is laser filtering. And for people that are not aware of the problem, there are lots of laser pointers around the world, and outside the presentation environment like this, people might use this, for example, in amateur astronomy to guide, to show the stars. But unfortunately, they are being used for other purposes, for example, to attack the police in riots. And also in the military is very common use of lasers to blind troops at night. The main problem we're trying to solve is that people use lasers and they attack aircraft at night and they blind the pilots, especially during the landing phase. And that's a big issue because it poses health risk for the pilots. You might damage their vision. It's a security risk for the aircraft, also safety risk for the passengers if the pilot is incapacitated of driving, of piloting. And also there are some economic risks, like whenever there's a laser attack, the airplane might be forced to abort landing or do a go-around, which has some financial penalties for the airlines. And this has been quite big of a problem in the last, I would say, 10 years. It has been routinely being reported in the last, every few months you'll see something on CNN about laser attacks in aircraft. And the issue is that, you know, the number of attacks that you see here versus time, it keeps growing. Last year, we had 7,700 recorded laser attacks just in the US. And this year, you know, currently we have 8,600 and it keeps growing. This estimate is a few months old. So just in the US, you know, there is a big issue and it's a matter of time before something worse happens.
So why is there a big jump? What happened?
Why is there a big jump? We don't know. I think it's more like this is a couple of years where this problem started being reported more in the news, and then, you know, sometimes it has the opposite effect. More people find out about it. We cannot be sure why, but I have a small video here from some events in Egypt from last year, a couple of years ago. It was actually not a laser attack, but this is the people's way of greeting the presidential helicopter coming into coming into the city. But you can imagine like something like this on an aircraft too, a kind of problem it might be. This was from a news story a couple of years back. And the problem is that these laser pointers are readily available now for everybody to use, and there's not much control. Why has this grown in the past 5 to 10 years? A couple of reasons: more lasers and more readily available for people to use. Also, they're much cheaper. Now you can buy a handheld 2-watt laser for less than $100, which is basically everyone can afford this. And if you look at the root of this problem, you might consider this as a post-telecom boom effect. So in the dot-com boom in the 2000, 2001, there was a lot of effort to develop optical sensors and sources that went into fiber optics. And then when all this died, all this technology sort of transferred maybe to handheld laser technology, and that's why the availability of the lasers started picking up soon after the dot-com boom. And that being said, the problem is very serious now, but it's not new. This is a 1979 paper from Hughes Aircraft Laboratories. It talks about laser eye protection for aviation. So it was starting being a concern back then. It's just a lot bigger now. So we saw this problem and we thought, okay, let's use our background on metamaterials and nanostructures to try to come up with a solution. Our main product we're developing is something called Meta-Air. So it's basically a windshield. This is a windshield of an aircraft that is tuned to reflect 532 nanometer laser light, as you can see in this photo. And it's basically a meter scale holographic notch filter specifically for aircraft. And we use holography to make them, and is a notch filter to reflect the, not just green, but all other laser colors as well. And we have a partnership with Airbus since 2014 to develop a custom film that goes on their aircraft.
So you're mainly covering the cockpit?
The cockpit, yes.
Right, okay.
Typically, a cockpit will have 6 windows that we need to protect. Excuse me?
It's otherwise transparent except for like 532.
Yes, correct. In terms of the optical requirements you need for this type of film, we need optical density 2 or more, so about 100 times attenuation. The band gap less than 20 nanometer in order to maintain good visibility. We need angular bandwidth at least plus minus 45 degrees, ideally even more. And the visual light transmission greater than 50%. This is how much light transmits on the other side. And these are the 2 key points that, maybe the rest you can find them with existing technology, but the last 2 points, you need to cover a surface area that is meter square. So one windshield is about, the cockpit glass windshield is about 2 meters square in total. And you need to be able to cover that. And, it cannot cost, millions to make. And also it needs to be neutral in color because the pilots sit behind it and they need to maintain good visibility and color accuracy as well. This is an example of how some of our filters look like. So here we placed our filters laminated on a transparent substrate, and we have a laser beam coming in, and we position it such that the left half of the beam is unblocked, but the right half, you see the reflection here on the film, and nothing transmits on the other side. And you can also see we put some color sheets behind so that to prove that you're able to see the colors accurately without without much distortion. And we spend a lot of time to fine-tune the coloration. We mix actually our nano structure film with dyes in order to get color neutrality. So here is an example of unfiltered photo. And this is how this picture would look if you look through, let's say, an eyewear for laser protection made with dyes. People also make them with deposition, and they are also quite pink in color. However, we are able to provide this filtering without having this saturation, the tint. Other than aircraft, these are also other applications for this laser filtering product. So trains are being attacked as well, especially in Europe, Switzerland, law enforcement for police, protective eyewear in the military, also defense helicopters, military, night vision goggles as well require often this kind of protection, and some more fun applications like self-driving car sensors where you don't want maybe shot to be blocked by some laser because it might throw off the sensor of the car. Now I'm going to talk.
Self-driving cars, what do they use for their positioning? Is it like video image or?
They use a combination of sensors, and some of them might be like an infrared camera or even visible one. And if you have a high source, like emitting, it will throw the sensor off. Now I want to focus more on the technical challenges of what are we facing in developing this product. We do use holography to make these films. The idea of combining two laser beams in a photosensitive material, and when the laser beams combine, you are able to engrave a refractive index pattern in the medium, thus creating a grating, a periodic grating that is tuned in a particular wavelength. And in a typical setup, you might have the two recording beams, and this will be your film, and you will have coinciding here the interference of the beams. We did try other methods like deposition before this. This was a better approach for the following reasons. First of all, is faster manufacturing. So you can record hundreds of periods in a matter of seconds. If you try to do that with deposition to have hundreds of layers, it might take you hours to do that properly. Also, it's scalable to over meter wide surfaces. Basically, you get a stronger laser, you expand your laser beam, and you can illuminate a bigger area. This is much easier than getting a bigger evaporation or sputtering chamber. Also, this is a film polymer-based product, the photopolymer, which means it comes in rolls, so it's easier again for production to have a roll-to-roll production. The film is also bendable, which means you can apply it to curved surfaces if you want, something you cannot do with hard sputtering materials. And also, you have more flexibility in the type of grating you record. And I'll give you a couple of examples for that. Some of the gratings we make, the most basic reflection grating, you have two counter-propagating beams at the same wavelength, and then based on the momentum conservation, the grating you form, has a particular periodicity and orientation. This you can do with deposition as well. Another thing you can do is, as you have these laser beams, you can rotate your field sample because you don't need vacuum for this. It can be done in air easily. So you record what is called a fixed slant grating. So now you're actually blocking at an incidence, for example, 45 degrees relative to your surface. This is something you cannot do as easily with other methods. There are other types of gratings you can do with holography. For example, if your counter-propagating beams come at an angle, you still record this kind of grating, but now with a spacing that is a bit longer, so it's adjusted for a different angle of incidence. And you can do the same for a slanted incidence as well. This angle of incidence selectivity is extremely important for this type of product. The reason being, if you look at how a cockpit looks like, so this is a CAD rendering of the 6 cockpit windows. These are how the pilots would sit, and we're trying to protect the area where the pilot's eyes will be during a flight. And is a complex problem to solve. These gratings have angular dependence, and we need to optimize the film in order to get the protection always within the specified area. And not only that, but the windshields are also inclined, so you have to consider both this geometry and also where the attacks are coming from the ground. This is a schematic from the point of view of the pilot, so the pilot eye would look dead center here, and this is how the windows appear from the point of view of the pilot. So for example, the captain position on one side, the left 3 windshields appear bigger, the other 3 are further away. And we want to optimize angular protection over this area. So for example, if you take this particular windshield, so it will have an angle is tilted about 55 degrees, and you want to protect down to 20 degrees from the ground. So the angles of protection relative to the window normal, you want to protect this area minus 55 to minus 35 degrees. So you need, if this is your glass, you need a grating that is sort of oriented to block in this direction. And the holography allows good flexibility to optimize this angle of protection. So although the concept of making a notch filter is simple, you have to tune it for the particular application. So overall for this Meta Air product, yeah.
So, how much of an index contrast do you need to really cover a fairly broad angular range, even like that? Of course, not a full hemisphere, but I think that, if you look at some of your competitors, like OptiGrade, usually they only cover very narrow angular range. So, but they also are creating very small index contrasts. So
yeah.
I guess the concern is maybe if you go to too high of index contrast, is causing unwanted reflection.
Yes, going to high index, the main problem is your blocking bandwidth is so large that it becomes too dark and tinted.
Right.
So our index contrast is quite small, but then we work with optimizing the gratings in order to get the maximum angular protection. So we do actually multi-layer gratings, which are not shown here. And also the grating we record is not uniform across the surface of the windshield. It actually changes as you move to different locations because it's optimized to block just for one position behind it.
I see.
So in this way, we're able to do small index modulation, and each point might have a small angular bandwidth, but considering where the attacks are coming from, the pilot is always protected behind.
Okay, now I understand your point.
Okay.
So it's actually a more challenging technical problem.
Yes, this is just the main concept.
Right. Right.
Yeah. So we're in the middle of a product here that in the middle of 2 areas that on their own are extremely challenging to do something commercially. So aerospace products have very tough certification procedures, and you need very robust manufacturing and performance. And also nanomaterial products are also extremely hard to fabricate with good tolerances over large areas. And our product is right in the intersection between these two. Yes.
Wouldn't it be better to just make goggles and coat them with these kinds of coatings rather than coating the whole of cockpit?
Yeah, so actually we do have a division that just does goggles. And these are easier to make, like we do have these prototypes ready. However, for the pilots especially, they don't like wearing the goggles. Their vision is perfect in their whole life. They never wear glasses. It's really uncomfortable for them. So their goggle is a last resort solution. They prefer a set it and forget it solution that goes on the windshield and then they don't have to think about it. Yes?
So is this a product is attached outside of the shield or the inside? Because
This is on the inner surface of the windshield, not on the
is there
outside.
any moisture issue when the temperature in temperature gradient between the hot and inside?
Yeah, so we account for this effect. So the environmental factors affect all films to an extent. There is temperature gradients, there is solar radiation, there is humidity. Also, most windshields are actually heated, so they're not at room temperature, they're a bit higher, up to maybe 40 degrees. These are all input design parameters that we take into account for when designing this. So to make this product, we've identified what are the challenges for metamaterial fabrication in general, not just for this product, but also for other products. So there are 3 items. Number 1 is you need good transparency for visible applications, so you do need to use transparent materials. Second challenge is large-scale nanofabrication, so we need nanometer precision over meter-long surfaces, which is something that's not trivial to do. Maybe you can do it on a small surface, but going large is not trivial. And finally, this needs to be cost-effective. So we've looked into this, and to get a product on the market, eventually the cost when you go to volume needs to be between roughly order of magnitude $1 to $10 per centimeter square in order to make sense financially as a business. We realized that early on, and all our efforts and fabrication methods have started shifting towards something that we can break down the cost to something like this.
Where does that number come from? It's billions or billions of dollars, right? So,
Excuse me?
so how do you arrive at that number?
So this number comes from how much we know how much the market is willing to pay for this type of product. Let's say for the windshield. Mm-hmm. So we can work backwards that in order the selling price, the fabrication price cannot be much higher than this in order to afford it. For example, if this was, let's say, $100 per centimeter square to cover, a 2 meter square windshield, you're in the hundreds of thousands and millions, and this is not the right price for that. But this is also true if you look at solar panels or LEDs, for example, a metamaterial film on an LED chip, which is, let's say, a centimeter square. There is so much you can pay for an LED bulb. It's a few dollars. So it cannot cost $100. Again, it has to be on this range to make it affordable.
I think solar cells have to be even lower.
Yeah, in the solar cells, the residential ones, yes, the price margins are even lower. For what we're interested in, which is aerospace, and they can command a slightly higher price. That's why aerospace is a good first market to try to approach. So to solve some of these issues, the large scale and the cost-effective fabrication, I'll move on to the technology we've acquired recently, we're developing, which is rolling mask lithography. So it's one way to do large-scale nanofabrication. The concept is that you have a mask placed on a cylinder. You fabricate the mask with a conventional method. This is your master. And then you roll it over a soft substrate. And then the features of the mask are engraved on the substrate. And on the photo here, you see our current rolling mask lithography tool is a 30 centimeters wide by 1 meter long films we can make. And is a solution for low cost and high resolution and large area nano patterning. We can use different substrate materials, and we can do a continuous roll-to-roll up to 1 meter wide web in the near future. The current resolution is about 150 nanometers, and we are looking to drop it down to 50 nanometers, which will allow us to do more visible metamaterial application. And is a relatively inexpensive tool, like costs about $1 million, per tool. And the throughput we're trying to will be able to achieve with this in the next couple of years is up to 40 meters square per hour, with a cost target of $5 per square meter.
Sorry, what's the difference between this technique and like roll-to-roll nanoimprint lithography?
So nanoimprint is slightly different. It works like a stamp maybe method, the nanoimprint, whereas this one, the features are on the mask, on a cylindrical mask, and then recorded on the surface here.
Yeah, I meant roll-to-roll. I mean, I agree the original nanoimprint was like a stamp.
Mm-hmm.
I think that there's been more recent work basically doing like something more analogous to that, like some sort of like rolling pattern that can be used for roll-to-roll printing.
Okay.
So I don't want to claim that yours is not novel, but I guess I don't totally get the distinction.
Yeah, I don't have a good answer for that yet because I'm not too familiar with the nanoimprint technology as much as with this one. These are some of the structures we can make using the RML technique, so different types of pillars and arrays of wires here. And I'm going to talk in particular, our main product is something called Nanoweb. It's a meter-scale, high-conductivity, transparent metal mesh. You can see some of the images here. We use different metals like aluminum or silver on glass. And this is a replacement for the conventional ITO, transparent metal meshes that are used in touchscreens or heating elements. And we offer higher conductivity, higher transmission with very good coloration that can be done in flexible films and different substrates. And very importantly, not visible to the human eye. So I have a small video to show you here. On that. This is basically a heating element. So this is covered with the Nanoweb. And then when you switch it on, it starts heating the glass. And you can see in the infrared camera here the response. The key point here is that we can have this heating glass without losing the transparency and very, very quickly. So this concludes the first part of the talk, and I'm going to move on to the second half, which is basically to make all these things, and how much effort do you actually need to get to a product like that? Because all is well and fine when you do it in the lab, but how much do you actually need to do? And here I'm introducing the concepts that whoever has done more project management will know, the concept of person month or person year, which is how much effort you need to put to achieve something. There is a famous book from, a couple of decades ago, the mythical Man Month. The guy was from IBM and discusses the point that, there were some software engineering projects at IBM, and then they threw more resources at them, like more people and more time, and they actually got worse results than you would expect with more resources. And the reason for that at the end turns out to be that, if you put more resources, doesn't mean things get done faster. Like, it's the same concept that, you know, a pregnancy is 9 person months, but if you have 9 people for 1 month, you don't get a baby out of it. You do actually need one person to work for 9 months. So it doesn't scale exactly. So inspired by this idea, the question I pose is, you know, how much effort in general is needed to achieve something? And we look at different things like get tenure, you know, write a fundable proposal, reach the first sale of your product, or commercialize an optical metamaterial. Like, how much effort do you need for that? And the idea I want to propose is that it takes more or less the same effort to achieve a certain goal. I'll explain what I mean by that in a minute. The more specific question I want to answer is that how many person years of effort are required to commercialize an optical metamaterial? That's a very useful piece of information if you know ahead of time, because if you're trying to do it as a company, it can tell you how many people you need to have. You can better plan your resources and also how much money you would need to achieve that. Before I answer that question, just to give you a better idea how this will work, I'll answer a maybe question that relates more to the academic audience. How many person years of effort are required to get tenure? So before I answer that, let's answer a even simpler question. How many person months of effort are required to publish a paper? So from the moment you start working on the project, how much effort do you have to put to get a paper published? Include not just the writing, but doing the research as well. So I looked at statistics of paper publishing from what's available. So just to give an example, if you have one author and that author produces one paper in 1 year, you can claim that you need 12 person months to publish a paper. If a single author writes 2 papers a year, that means there are 6 person months per paper. Correspondingly, 2 authors, 1 paper in 1 year, it means double the effort, 24 person months. And 2 authors, 2 papers per year, 12 person months. I think this gives you a feel how this is going to go. So I looked at the statistics of some tenured professors in the academic industry, and you can see how many papers they publish per year, how many authors, and you can divide all that, and the answer, the number is about 2.1 person months per paper. So if you were one person and working on one thing, it would take you about 2 months to do the research, write the paper, and publish it. And the error bar here is about one person month, which is quite big. And there is actually a big difference whether you're doing theory or experiments. You'll see for experimental papers, you're more on the higher end of this. Theory guys tend to publish a bit more frequently. So starting from that, we can answer another question: how many person years of effort required to get tenure? So basically, I looked at the tenured professors and look at their publication history, and you sum all these things up, and you see how many papers they had to, how much effort they put into publishing their papers. And the answer is 29 person years plus minus 2. Now, keep in mind this effort here, obviously you have co-authors, you don't publish all this by yourself. But it's interesting if you think that like one PhD, let's say, is 5 person years, you work by yourself for 5 years. This number tells you that you need to do 5 more PhD difficulty projects to get into tenure. So if you think it's easy after you graduate to get tenure, think that you need to do 5 more PhDs basically. Obviously you have a research group to help you in that, but that's the main idea. The interesting point here is that the error bar is now much closer. So across different fields and different areas, to get tenure, is more or less the same effort. You cannot escape that. There's no simple, easy way out. And this is, I should mention, this is for like high-profile US universities, the effort required. So moving now from the academic to companies, how much effort required to make something when you're in a company. So just to give you some sense of scale, 30 person years is to get tenure, and we compare that to some other projects, like big engineering projects, the Burj Khalifa and Panama Canal is 2,500 person years to be built. The Channel Tunnel in Europe between UK and France was about 80,000 person years. And sort of the biggest projects of all, Manhattan Project or Apollo program, is about 2 million person years of effort. So where in the scale do we find the effort to commercialize a product? And to answer this, I looked at hardware companies, because there are no commercial optical metamaterial companies that have actually sold many products, but I did look at hardware companies, how much they need to get first sale, and I have 3 examples. The first one is Nest, the smart thermostat. The company started in April 2010, and they were able to get to their first sale a year and a half later. They had 75 employees at the time, so the effort to get that was about 105 person years. Already you start getting a sense that, even for something relatively simple like this one, you need like 100 people for a year, let's say, to work and publish this and get this. Another example in the iPhone, it took Apple about 2 years, and they had 2.5 years, and they had 250 employees working on this. It was about 625 person years from when they started until they managed to sell the iPhone. And a final example is Tesla. The company was founded in July 2013. They started selling their first car, the Tesla Roadster, February 2008. They had 250 employees at the time. So that's about 580 person years. So using this, the conclusion I want to draw from this part of the talk, if you're trying to answer how many person years of effort are required to commercialize an optical metamaterial, it's more likely along the lines of like a Tesla Roadster or the iPhone. So I would like to claim that the answer is around 500 person years. So that gives you an idea if you want to start a company or commercialize something, this is the kind of effort you need to put into this. It's not very simple.
So how much money does that equate to then?
It depends. So the money is a few tens of millions, a bit less than 50 usually. Again, this is just it's very speculative at this stage. Was just relying on some statistics, but ballpark, that's where you should think that. So just the salaries of 500 people, let's say for 1 year, is on this order.
So that could be a challenge for raising VC funding, I guess. Yes, and that has been a challenge for us as well. The idea is the way to get around this issue is that you want to release maybe something simple first before you go to a more complex full solution. That's why in our case, the laser filtering is like a lower hanging fruit, which on a relatively simple nanostructure that we can make, hopefully with a bit less effort than this one. For example, our company for now is around 80 to 100 person years of effort in the last 5 years.
I just have one final slide in my talk, and this is, comes back to the idea, how easy it is to make something, and people get usually discouraged often that what I'm trying to do is harder, and I will not be able to do it, and then I am in that position very frequently when we make something we think is not very easy to do. And then I imagine myself talking to, there is a sculptor named Giovanni Strazza, Italian sculptor. So he made this piece of work. It's called The Veiled Virgin. So whenever I find myself in a tough position, I imagine him showing up, showing me this, and then telling me, Themos, I have made marble look like transparent veil, so you can do this. This is a much harder thing to do. And that concludes my talk, and thank you very much for your time and attention today.
Thank you, Themos. Very unique perspective.
Okay.
Very happy you came. So let's see if we have time for a couple of questions.
Yeah. I'm glad people asked questions as we were going along.
Yeah.
I think it's better. Yeah. Yes, please.
So you determined that there was 2.1 person months on average per paper?
Yes.
So that's just dividing by the total number of authors? Right? Did you try and account for the fact that maybe out of a group of 10 authors on a big science publication that maybe some of them are just there in an advisory role and don't actually put the
Yeah, so I did not weigh the contribution of the different authors, so everyone is equal in this. Obviously, this is not true. It's almost never true. And I just didn't have time to go into this second level detail.
Well, I'm just wondering when there's like 1,200 authors on the LHC papers.
Okay.
So only a few months of person months to get the LHC up and running.
Yes, I consider the LHC papers as more extreme cases. I didn't include this kind of statistics. I took more in the field of engineering and science, where you usually have the average number of authors in the papers I looked at was between 4 and 5. Yeah.
Can I ask how much effort has your company put into your product so far? So, how far are you from getting your first sale?
Yeah, so I think I mentioned we're about in the 100 range, 100 person years. And hopefully the product we're making is simple enough. We don't need to go to the 500. It will be sooner than that. Part of the reason we can do that is we outsource some of the work that to other, let's say, subcontractors or other vendors. And we do more the core, fabrication thing, what's different. Tesla did something similar with their cars, until this year, I believe, all their batteries were made by Panasonic. And just now they're building this gigafactory that they make the batteries in-house. So basically, you buy some of this effort, and you don't have to do it yourself.
So if it is 500, you survive?
Yeah. So it's
500 instead of 200?
It should be okay, yes. I'm pretty sure we'll probably need around 200 and not 500. Again, because the product we're making is not as complex as a full optical metamaterial like the ones you probably make here.
So is that another 5 years?
Oh, no. Our head count, for most of the history in the company, we're just a handful of people. This year we grew to 20, and we'll probably double in size by next year. So actually, if you look historically, these examples, how their effort is distributed over time, not just the average, they all start low and then it spikes near the end. Yeah.
So any other questions? So I have a quick question about, in terms of the economics.
Yep.
So roughly 200 person years. So how big is the market to justify in terms of the like? Is that I'm sure you have worked out the economics, so I'm just curious. How big is the market?
Yeah, so for the laser filters for aircraft, for example, there are about 30 to 40,000 like commercial aviation aircraft, the type of aircraft everybody uses to travel around. There are way more aircraft like for transport or much smaller aircraft, but this commercial aviation is in the tens of thousands. So, and eventually we want to capture all that market. Like there is a good chance if the attacks keep increasing, this will become like a safety standard that needs to be included in all these aircraft. Much like the seat belts are for cars now, you might require this. So at the beginning, we plan to start production next year on this. We'll be able to do, couple of thousand aircraft per year at this stage.
All right. Thank you so much, Themos.
Okay.
And let's thank our speaker once again.
Thank you.